Okay, well, that's all she wrote for breaking down fats. But what about the other side of the coin? What about building up fats? Um, acetyl CoA is the precursor here, and fatty acid synthesis is going to take place in the cytosol. Uh, and this seems weird, right? Because wasn't our whole point is that CoA is not ever allowed through the membrane, right? So how does that work? We have another shuttle, right? We just have another shuttle. So we use citrate as a temporary intermediate, which can move through the membrane, and then we just turn it back into a CoA. So acetyl CoA in the Krebs cycle combines with oxaloacetate, OA, the very first step, and it makes citrate. And usually the citrate, goes isocitrate, goes to alpha ketoglutarate, but the citrate can leave. It can go through this little nice citrate shuttle. It's allowed through. Okay, that's it. We don't need the citrate anymore. The only point is to get it through. So let's just convert it back to acetyl CoA. Boom. Wait, how do we convert it back to acetyl CoA? Which is the exact opposite of this process, right? Acetyl CoA combines with OA to make citrate. So if I want to break apart citrate, it's just going to give me one OA and one acetyl CoA. All right, now OA fucks off. We're done with that. So now the acetyl CoA, for reasons I don't understand, we have to do a little carboxylase thing. And whenever we have a carboxylase, boom, we got biotin. So acetyl CoA makes malonyl CoA, which is then going to further be built up into larger like palmitate type structures, which we'll talk about in a second. Keep in mind that malonyl CoA is a major inhibitor of the rate limiting step of fatty acid breakdown, right? The other path, the catabolic pathway, not the anabolic pathway. Why would that make sense? Because again, you don't want to be crossing the streams. Why would you be doing anabolic and catabolic at the same time? So it makes sense that if you have a lot of malonyl CoA, it's an indicator that you're probably doing fatty acid synthesis, in which case you don't also want to be doing fatty acid breakdown. Where does fat, where are we making fats? Liver does any sort of metabolic thing, right? It can make fats, put them in VLDLs and send them into the rest of the tissues. Lactating mammary glands, for reasons I don't really understand. And then adipose tissue, obviously, that's the whole point. Let's just store the fats there. All right, let's just keep in mind, we want to do gluconeogenesis. Pyruvate, for whatever, the last enzyme of a glycolysis is irreversible. So we got to go through a different route. For some reason, we got to carboxylate it to make it OA before it can be shipped backwards through gluconeogenesis. This one's also weird, but I guess can kind of understand it a little bit. Propynyl CoA is odd chain fatty acid, is something that usually you end up with acetyl CoA, but 10, 8, 6, 4, 2, but now we have 11, 9, 7, 5, 3. I feel like that's a test like an officer would do if you had a DUI, right? Instead of do the alphabet backwards, they're like, do this beta oxidation thing backwards. So this is another one for the propynyl CoA. We have to make it methyl malonyl. Remember, malonyl is 3 and methyl is 1, so this is 1, 3, 4. And now here's the last one, acetyl CoA. And of course, all biotin B7. Acetyl CoA is made to malonyl CoA, is something we're going to ship into for fatty acid synthesis. So now we're going to do beta reduction. And this is really just the opposite of beta oxidation, right? Remember beta oxidation, put in acetyl CoA in the mitochondrial matrix. We do oxidation, we do hydration, oxidation, and then we use sulfur to basically break, not break in half, but break off two. Break off two, break off two, break off two. Well, this is beta reduction. So it's really just the exact opposite. This is happening in the matrix. This is happening in the cytosol. Remember, acetyl CoA is not allowed out, but we make it citrate, and then we take it out, and then it's acetyl CoA, and then it's malonyl CoA, and now we're doing beta reduction. So this is exact opposite. We're going to be reduction, dehydration, reduction, condensation. Condensation meaning adding to. I'm not even really going to go through all of this, but we have an acetyl CoA and a malonyl CoA, and repeat 7 times, right? Why repeat 7 times? Because we're making a palmitate, and we're starting off with 2. So, if taking 16, 14, 12, 10, 8, 6, 4, I swear I only had 2 drinks, officer. 2, right? That's only 7 cycles. So going the reverse would be the same, right? 2, 4, 8. Wait, 2, 4, oh my God. 2, 4, 6, 8, 10, 12, 14, 16 is also 7 cycles. So just the exact opposite. That's what I would know. I would know mostly we're going to make palmitate, which is a saturated fatty acid. Why? Because there is no double bonds there. 16 carbons long. pretty much the same thing, right? We're taking an acetyl-CoA, an OA, we make it a citrate. Why? So we can shuttle it through. Okay, we're done with your citrate. Let's get back to our acetyl-CoA. We're going to push off this little OA there, which can probably go back. Here's our acetyl-CoA. For reasons that are above my pay grade, we're going to use biotin to add a carbon group. Malonyl always means 3. For some reason, this is an input. So now we take this malonyl, blah, blah, blah. We put it into beta reduction, exact opposite of beta oxidation. Now we have an acyl-CoA. Acyl just means fatty acid. Probably palmitate, 16 carbons long. Now this could happen again. We said this can happen in lactating breast tissue. This can happen in fats. Let's just imagine this one's happening in the liver. So if this is happening in the liver, maybe we want to ship this to the fat so then the fat can store it. So we're probably going to put it on a VLDL, which is holding a lot of these fats, and then we can ship it to the fat, which can store a little bit more permanently. So now it gets to the fat, and we need to, the same way we had fatty acid mobilization, which is like, let's break down a triglyceride. Glycerol goes to the liver for gluconeogenesis. The 3 fatty acids go to albumins, and then they can go to the liver or the muscle or wherever. Remember when we're ripping off the fatty acids, we rip them off one at a time. This is the exact same. We're gonna add them one at a time. So an acyl-CoA and a glycerol, we're gonna add 1 and then 2. And remember that when you have 2 fatty acids on a glycerol, it's basically just a phospholipid. So you can make a phospholipid, or you could keep going and you get to a triacylglycerol. I don't really think you need to know, we're just know it's 1 at a time. I don't think this is that high yield. And then just kind of a review. So we have an adipocyte. We want to store our triglycerides here. You could just push glucose in. The glucose could make DHAP, which is just DAP. That can make glycerol. But you can also, glucose can go ahead and make pyruvate, which can make acetyl-CoA. Acetyl-CoA can make fatty acids in the adipocyte. And then those could, here's our acyl-CoA. And these could combine, you add 1, you add 2, and then you add the third one, and now we have a triglyceride stored here. However, we're probably going to have very, very little. Glucose probably isn't going to be making the majority here. The majority of this is probably fats you just ate like a, big fatty steak or something, fried chicken. Or a VLDL is that your liver's already said, hey, it's a good assistant. It's like, I already did all the work for you. You just need to cash it in or store it or whatever. So the VLDL has made the fatty acids, stored them in this little lipoprotein particle, ships them through the blood, and now the fatty acids come in, acyl-CoA is just a fatty acid, and it's going to be combined, and again, triglycerol. Review, summary. All right, so we have acetyl-CoA to citrate. Why citrate? Because it's not allowed through if it has a CoA. Boom, we push it through, goodbye citrate, we're back to acetyl-CoA. Reasons I don't understand, we add 1, we got malonyl-CoA. Malonyl-CoA goes through beta oxidation, we got our palmitate. Remember that malonyl-CoA, if we're doing synthesis, we probably don't also want to be doing degradation. So what about the degradation? My muscle is very hungry now, so we're shipping it a bunch of fatty acids. And you know what? If a cell has a lot of fatty acids, we're probably doing degradation, and so we don't also want to be doing synthesis. Also, though, another way to interpret this is that we've just done enough synthesis. We made enough of these, and so this is just classic negative feedback. That might even be more common. I don't know, but just no fatal fatty acyl-CoA. Acyl-CoAs can inhibit that. Anyways, back to here. We have our fatty acyl-CoA. Oh no, CoA is not allowed through the membrane. What are we going to do? Well, instead of making citrate now, we just have the car for shuttle carnitine, which is, CPT1, rate limiting step. Put the carnitine on. It's now allowed through. Immediately CP2, CPT1 and CPT2, also known as CAT1 and CAT2, right back to back. Put the carnitine on, take the carnitine off. Okay, now we're back to a CoA. Now just beta oxidation, oxidation, hydration, oxidation, thiolysis. We have an acetyl-CoA. This can go to the Krebs cycle, or if in your liver, you can make ketones bodies. It's in that everywhere, but especially important, the brain and the red blood cells get some. All right, so I have not eaten in a couple hours. I am using a lot of... So you're always, let's just make a point. You're always breaking down like proteins and fats and sugar at the same time. It's never trinary, right? It's complex, like a little bit of all of them. So when we do this, we're really simplifying it and this is probably what you see in the test. So we can imagine that if you have not eaten in a few hours, your body is just using the free glucose in your blood, or the muscles have their own glycogen and the liver has glycogen it can break down and send to the body. That is probably the first thing. Now, if you haven't eaten in like a couple more hours, like 16 hours or so, really in the first. So first is glycogenolysis. Then a little bit later in the day, you're still doing glycogenolysis. You start doing gluconeogenesis. Again, we're always doing gluconeogenesis, but you're doing way more gluconeogenesis than you were. Remember, this is the MacGyver. We're just taking glycerol. We're taking amino acids. We're taking just random shit in the liver, making new glucose, pushing into the blood, feeding everybody. But you run out of your carbon stores really quickly. So meaning mainly your glycogen. All right, so now the next week or so, you're doing gluconeogenesis. Wait, didn't we just say we're running out of carbon stores? Yeah, no, carbon stores, glycogen. Gluconeogenesis is the MacGyver. We're taking glycerol, we're taking all this random shit. So you're still going to be doing gluconeogenesis, and then you're going to start breaking down your fat. So now, of course, this is going to vary. It just depends how big you are, right? How much extra meat do you got? And then eventually, finally, after a couple of weeks, your body's going to really start making a lot more ketones, especially because the brain and the red blood cells have a hard time dealing with the fat. So carbohydrates go first. Depending on how much fat you have, that goes next. And then protein. Protein's like really, you spent a lot of time at the gym trying to, build some good biceps or something. Your body's aware of that. And it's like, last thing I want to do is shred our biceps because we're like, hungry and starving in the Amazon. But at a certain point, it's like, fuck your biceps. We're going to break down that stuff. And of course, not just your biceps, but like proteins are important. It takes a lot of effort to make them in any cell. And so we really don't want to break them down unless we absolutely need to. That's why proteins go last.